Welcome to the second week of the C# application development class. And what this module is really going to cover this week is the object-oriented kind of nature of C#. It's going to talk a little bit about object-oriented design. But in this first lecture, what I want to do is kind of go through the theory and how object orientation works inside of the language. And then in the other content, what we're going to really do is focus on actually showing how some of these how some of these concepts work by actually coding and hopefully completing at least a rudimentary task management system. So this is going to be kind of an introduction to object-oriented programming. I'm going to pretend like you know minimum information about object orientation. It's going to be very, very familiar. I'm going to try not to get lost in the weeds so much, but really just provide kind of a general overview of what object orientation means, what it gives to us, and how you do it in C# specifically. So last time, to kind of contextualize what we're talking about, we talked briefly about basic syntax. So we went through kind of the 10,000 foot view of the language, looking at things like operations, like conditionals, like repetition with loops, and a lot of the general concepts associated with .NET. So talking about the fact that C# is fundamentally the same as Java in terms of running inside of a virtual machine, except instead of trying to support cross-platform with that virtual machine, what it actually does is tries to give a different it's the same functionality to a different set of languages effectively. So VB.NET, F#, all of these languages have access to the same libraries, largely because they run inside of the same sort of virtualized environment. So at the end of that conversation, we started talking about what I kind of briefly referred to as the idea of encapsulation. So you can have things that are called methods in C# that function the exact same as functions in C or C++. And we kind of left it at that. And so this week what we're going to do is we're going to talk about objects and classes and how methods interact or are associated with objects and classes, and kind of fill out what object orientation means for C# as a language. So we touched on this briefly before, but in C#, everything in its entirety is object-oriented. This is very similar to the way that Java is constructed. So if you think about it a little bit, you've already kind of seen how object orientation or the basis of object orientation works inside of C#. Even with something as simple as your first programming assignment where you basically built a very tiny point-of-sale system, you still had a class, you still had a main method, even if you didn't use methods for encapsulation to further abstract or further encapsulate the business logic that you were trying to use. At its root, you were still using a class, and you were still using object orientation. So as with every other language, kind of modern language that supports object orientation, the concept of a class is effectively just a template that you can use to create instances of that class, which are called objects. So while you might have a car class that implements all of the data, so for example, the year of the car, the make, the model, the color, all of that kind of stuff, and the behavior of the car, so speeding it up, slowing it down, parking it, putting in neutral, all of that, you can also, from that class, create specific cars. So you could have an instance called my car, and my car could be some old Ford Taurus or whatever you want it to be, and that could be different from someone else's car. So even though the cars have the same idea of what state is required of a car and the same idea of the behavior that a car can do, they don't necessarily have to be the same car. You can have hundreds of millions of cars. They act the same, they walk the same, they sound and taste and smell the same, but they're not the same car. They're different instances of the same general idea. So this is the fundamental kind of base upon which all object-oriented programming and design is built on. So if you misunderstand this, then the rest of everything is going to be really kind of confusing. So if at this point I've kind of lost you, you're probably one of the 2 or 3 people in the course who haven't really taken something like data structures before. Maybe you've heard the idea of a class and an object. You don't really get it. If you need some more kind of steering, please let me know. I'm happy to walk through a bit slower. So inside of a class, so on one of these template kind of ideas, you can have different types of what are called members. So a member for a class is basically a thing that hangs off of an object of that class. So we can think of these as 2 buckets of items. One of them is a field or a property, which exposes state. So this is all of the make, the model, the year of the car, all that kind of stuff. And you also have methods which expose the behavior of objects that are created from that template. So for our car example, it could be braking the car or accelerating the car or whatever. And so each of the members, be they fields or properties or methods, they can have access modifiers, which tell you what other classes and what other methods have access to them. So they can be public, which is exposed to everything. They can be internal, which is exposed only to the same assembly, which we'll get to in just a second. Or they can be private, which is exposed only to the same class or the same object. And each of these things can choose to use the static keyword or not. And so we touched on static just a little bit last time. We're going to go into a little bit more depth this week. So that depth is basically if you have a static method or you have a static field, those things are accessed from the actual type, that is the class itself or the template. Other non-static members, fields, properties, or methods are accessed from a specific instance of that class. So you wouldn't necessarily want the accelerate or the decelerate methods to be static because you want each car to be able to accelerate and decelerate by itself. You don't necessarily want all cars in existence to accelerate and decelerate at the same rate. Likewise, you don't want the make or the model or the year to be static because you want each instance of the class or each object to have its own state, not necessarily shared state across all cars in existence. So if you think about it, that's really how you should determine if you use static or non-static members. So if you want it to be shared across all of the objects of that type, so the behavior or the data, you can make that thing static. If you don't want that behavior or that data to be shared, you should make it non-static. So in addition to that, there are some performance penalties that you pay for having static members on classes in C# specifically. And basically, anytime you make a function or a field or a property static on a class, you are taking up the space required to implement that, regardless of if you were actually using it or not. So there's kind of a greedy load situation going on with virtual or with static members that does not happen with non-static members. So we spoke just a minute ago about assemblies. So assembly is kind of a word that gets thrown around a lot in .NET and elsewhere. And basically you can think of an assembly as a file that is created by the compiler. So any file that's created by the compiler, you can basically just label it as an assembly. And basically these things come in 2 different flavors. So the first flavor is an executable. These things are .exe files, and they are runnable directly from the operating system. And so these are very similar to C++ applications that have a main method. These things have entry points. And basically the operating system can use that entry point to actually run the code and do whatever it is that the code is designed to do. The alternative to an executable is a dynamically linked library, which has a .dll extension, and these work exactly the same way as C or C++ libraries. They don't have an entry point, but they can be referenced by code that does have an entry point, which is an executable. So you have something like an application that is an executable. You have something like a library that is a dynamically linked library in C#. So inside of an assembly, you have this concept of a namespace. And so a namespace, all it is a logical name that's given to pieces of an assembly. So you can have a whole bunch of different namespaces inside of an assembly. So that's a whole bunch of different logical buckets that are inside of the assembly. You can think of these things as almost like hard drive partitions that you're labeling. So basically these things are for organization purposes more than anything. And so you can give each file, each .cs file in your compiled file a namespace of its own if you want, or you can use them to group classes together. And so the way this works with C# solutions or projects is that each project is either going to compile to an executable because it has been marked as a console application or a WPF application or whatever, or it's going to compile to a dynamically linked library because it's been marked as a library file. And the .NET compiler named Rosalind is going to know which of those files needs to be created for whichever solution or for whichever project. Inside of a solution, you can have multiple projects, and we're actually going to go through that, if not in the code along this week, next week. And what will happen is when you build the solution, all of the projects inside of the solution will be built, and then you could potentially have 3 or 4 libraries that are all referenced by an executable, and they all are self-contained inside of one Visual Studio solution. At the end of the day, you have to have a namespace for every class, and you have to have a namespace for an assembly. So what you get as a result is that you don't actually have global variables inside of C#. There's not a concept of a global variable. And the reason is because you cannot have a member, particularly a field or a property data member, at the namespace level. You have to have it associated with a class. So in order for a variable to exist to begin with, it has to be associated with a class, and regardless of if it is static or not static, without the class definition, you don't have access to the variable. And so essentially, it has to have a class in order to exist. If it doesn't exist, then it doesn't have a class associated with it. So the bottom line here is that you can emulate a global variable in C# by accessing a centrally located class. So you could name a class global, for example, and on that class, you could put a whole bunch of publicly available properties or publicly available fields. And that would serve the same purpose as a global variable as long as it was in either the same namespace as everything else, or it was referenced across a namespace using a using statement, which we'll get into a little bit later. But all of the same concerns that exist for global variables in C or C++ or Java or any other language would be present for that design. So there are specific reasons why you don't necessarily want a whole bunch of global variables. And those same ideas would effectively apply to the situation where you emulate a global variable by making one centrally located class have a bunch of public data members. So what you get at the end of the day is that C# itself and the design and the implementation of applications inside of C# is so sort of intricately linked or inextricably linked to object orientation that you can't really get away from object orientation when you're trying to build a C# application. So what ends up happening is when you are a member of a .NET shop and you're just kind of trying to build whatever system you're trying to build, and you're linked to C# or F# or whatever you're trying to use, the choice of design is often inextricably linked to the language that you choose. So if you're trying to build a .NET application that is functional in nature and not object-oriented, you would obviously choose F# rather than trying to make C# bend into a more functional design methodology. So when you're working in C#, if you're trying to build something that is not object-oriented, basically all you're doing is trying to bend the language to your will, and in some cases that will work. In a lot of cases, you're basically just setting yourself up for failure. So the idea behind this type of design is you basically want to take whatever application you're trying to build, and you want to decompose that application domain into as many of these very tiny classes that you can, and then model all of the relationships between the pieces of the actual real-world experience as classes, and then method calls or inheritance or whatever other relationships you have in code all emulate the relationships between those individual pieces in the real-world scenario. So the grouping of classes that you use to emulate a real-world scenario in order to build an application to support it is often called the object model. And if you are trying to build an application and you find yourself trying to expose a whole bunch of public variables on a whole bunch of different classes, and those public variables are referenced all over the place. Typically what that means is that your object model is warped in some way and is not necessarily set up in an efficient way. So this is particularly important when you're trying to create a very large application, and the job of a software architect is to go in and make sure that the object model itself is made as efficient as possible by setting up what are called class boundaries and ensuring that the level of encapsulation, so the amount of business logic that is put inside of each method, is reasonable. And so reasonable gets giant air quotes because it's kind of a contextual situation. So the takeaway from this slide, or the takeaway from this part of the discussion, is that the object model is fundamental to any development that you're doing inside of C#. And if you put the object model out of your mind and you continue to develop kind of the same way that you would maybe in C or a more procedurally driven language, you can make things much harder on yourself than they would otherwise be. And so as you go through the course, particularly in the code-alongs, you're going to see that it's very easy to break ideas into objects. And if you don't start thinking about that, what you can end up with is very large classes, and those very large classes can have interdependencies, and then your code becomes very, very hard to maintain. So in C# proper, there are two ideas that are basically the same. These are classes, and there are primitive types. The clearest example of this is the string with a lowercase s type and the string with a capital S class. The difference at the face of it is extremely minimal. Really, optimizations at the memory level can be done using one versus the other. But basically, they're the same. They share a lot of the same use cases, and it's kind of hard at this level to see the differences between them. But what that means is that types, these primitive types, kind of illustrate how classes themselves are instantiated inside of the language. And so when you create a class, that class can be used anywhere a type can be used because they're effectively the same thing. And so by virtue of being the same thing, you can think of a variable as an object that's an instance of a class, and it kind of makes everything easier to conceptualize. So In order to create an object from a class in C#, you're going to use the new keyword, and that keyword is followed by a call to a class's constructor. This is exactly the same way that Java works. The syntax is exactly the same as Java's syntax. And basically a constructor is just a special method that returns an instantiated object and not like a primitive type or a return value or a return type. So every class in C#, regardless of if you have given it one or not, has a constructor. If you have not specified a constructor, the class will have a default constructor, and the default constructor is always invoked with the syntax new followed by this method. And so this is the syntax of the default constructor. It's just the name of the class followed by empty brackets. If you wanted to create an instance of this of a class or an object using this constructor, you would have new and then class name and then a semicolon, and you would be done. So the default constructor, what it does is it goes through all of the data members. So it goes through each of the fields, it goes through each of the properties, and it makes sure that the backing fields of all properties or all fields are filled in with their default value. And so nullable types have a default value of null. Integers have a default value of 0. There's a huge table that you can actually look up that will tell you the default value of all the primitive types. But at the end of the day, what you get is an issue that we're about to talk about, where you can have a default constructor that specifies a default value onto a field that results in a very common exception called the null reference exception, which we're going to spend a little bit of time talking about because you are certainly with 100% certainty going to experience this situation at least 1 million times in the course. You're probably going to run into it a handful of times just in this week's programming assignment. So the kind of conversation about null references. So classes themselves are reference types. And so what that means is when you are trying to make a class and you have a data member on that class that is also a class type. So it's not a primitive type, it's another class. What will happen is that property will get stored as a pointer to a memory allocation that will eventually store a piece of data that is the shape of that class. So this eventually is bolded because that is not necessarily something that is set up right away. And so what will happen is if you call a default constructor and you have a whole bunch of different class types as fields or as properties on that class, what will happen is each of those reference types will be set to a null pointer. So the good news is that that minimizes the amount of space that's required to call the default constructor on any class to create a default object. However, it opens the gate to this null reference exception situation that we're going to try throughout the class to kind of avoid. So anytime that you try to access a property on a class that has been referenced by a null pointer, you will get a null reference exception. And so an example of this would be if I have a student object or a student class and I wanted to specify an assignment on that student. So I wanted to have a property that is maybe the best assignment that that student has ever turned in the course. And I don't set the assignment property of the student to a default assignment in the default constructor of the student, it will be a null pointer. If I then try to access the date that assignment was turned in, I will get a null reference exception because I tried to access data on an allocation or on a memory space that wasn't actually set up to begin with. It was just a null pointer that doesn't actually have access to a field. So this is going to make more sense in the code along, but prepare yourself to see this quite a bit. So in general, this is by far the most common exception in even production code that is running right now. And the bad news is that once the exception is thrown, unless you have a try-catch or unless you have something to stop the exception from propagating, what will happen is the entire application will stop and the application itself will be forcibly closed. Now, if you're only building console applications and you're only dealing with desktop type development, that's kind of okay. The problems that we're going to run into, though, are when you're trying to make a web call from a client machine to a server, and this null reference exception happens on the server. What will happen is your entire web call will fail. And so even if this null reference exception is on something stupid, like accessing the last modified property of an object, and you're never actually really even using it, it will render the web call completely useless. Nothing will actually work after the exception is called. So these are the most common source of breaking changes, for example, and they're a huge headache. And they're actually such a huge headache that next week, when we talk about kind of advanced language features or language syntax, we're going to look at a specific thing called null propagation, which helps you get around this situation and kind of suppresses null reference exceptions a little bit to reduce the amount of null handling code you have to generate. Because in order to handle all possible null reference exceptions in every piece of code would mean that you would have to have a try-catch around every access of every property that's a reference type in your entire code stack. And that would be a lot of try-catches. So null propagation, the idea is to allow for a little bit more graceful handling of this very, very, very common situation. So proceeding down the kind of object orientation pathway here, class abstraction is basically the name of the game for anything that you're trying to do with object orientation, regardless of the language that you're trying to use. And basically the idea is that you want to take your bank or your restaurant or your whatever you're trying to emulate to support an application, then you want to break that object model into as many very small objects inside of an object hierarchy as physically possible. And you want your object model to actually reflect reality as close as possible. So there are all these tricks that we'll go through later in the semester when we specifically start talking about design, where you can take some kind of hypothetical shortcuts that kind of help out a lot. But in general, what you want is you want as detailed object model as possible, because if you have a detailed object model, even if you don't use all of the detail, you can easily generalize that object model to fit reality better than trying to shoehorn functionality in at a later date. So one thing to note that is very different from C# and other languages that support class abstraction and object orientation is that while C# handles abstraction through inheritance and through the implementation of interfaces exactly like you would expect in Java, it does not allow multiple class inheritance. So you can't have multiple parents for the same child class. However, at the end of this lecture, we're actually going to talk about a sort of workaround, and then there's also going to be a specific code around video talking about that workaround and how it kind of works. So, inheritance. The idea here is to put as much core functionality into what are called in C# base classes as physically possible. So if you are looking at building a POS system or point of sale system, you basically want a whole bunch of items. There's like a general idea of a thing that you can buy, and then you can build increasingly more specific items that inherit from item, and all of those items will have the same core functionality. So they'll all have a price, they'll all have potentially a buy more option or a get name or a get functionality option. And then increasingly more specific child classes will implement more specific functionality. So they'll expose more behavior, or they'll overwrite behavior of the parent, so on and so forth. And so there's a sort of very old, very tired example of having an animal class. And so you start at the very top and you have just an animal base class, and that class implements all the shared data that is shared across all types of animals. So for example, you would expect all animals to have an age, you would expect all animals to have some sort of eat functionality, you would expect all animals to have some sort of sound that they make, etc., etc. And then you can go one layer deeper. So one layer deeper might be a derived class for specifically birds. And so birds would have something specific to them, like a feather type. You wouldn't have feather types on all animals. It would only be for birds. And you would also have specific behavior, like laying an egg. You wouldn't necessarily want mammals to be able to do that. So that functionality would be on the derived class for specifically birds. Then you could potentially continue this cascade effect. So you could have an additional class for parrots, and parrots may be able to speak while other birds cannot speak, and so you would have a specific piece of functionality on a parrot that allows it to say something, and then you could even have even more specific types of parrots, and this thing kind of telescopes for forever, or until you run out of use cases in whatever application domain you're in. So the good news is that inheritance syntax in C# is really, really easy. Basically, all you need is to add this colon and whatever the base class name is to the derived class. What this will do is it will allow you to call any of the properties or any of the methods on the parent or the base class from the child, and it will also let the child override any of the base class's virtual methods, which we'll get to in just a second. So one of the things that I try to do in all my classes is kind of embrace the fact that everything in the world kind of exists on a continuum. And so if you think of class abstraction as kind of a continuum, you can think of two ends of that continuum. On one extreme, you have static classes. So static classes can only have static members. That means that all of their methods and all of their data or their fields or their properties or whatever have to be static. And because of this, you cannot have a class derived from a static class. So if you have a static animals class, that's where inheritance ends. You can't actually have a bird or a parrot class because all of the functionality is centralized at the type level for a static class. At the exact opposite end of the spectrum, you have abstract classes, and abstract classes have abstract members, and typically this is members only, and these things have to be inherited and then implemented by a derived class. What this means is that an abstract class not only can provide virtual methods that are overridable, they have to be overwritten or they will not have an implementation at all. So somewhere in the middle are regular sort of base classes that might have some static methods, but they also will have some virtual methods that can be overwritten, but it's not a requirement that their derived or children classes override that behavior. Sort of stepping back to abstract classes, turn the lights on here. All of the members of an abstract class must be abstract, exactly like all of the members of a static class must be static. So abstract classes basically don't provide an implementation of any size, shape, or variety. They are specifically created to be overridden by a child class. So this is basically a logical grouping of method prototypes. Those method prototypes have to be implemented by a child class, however that child class sees fit. So these things, abstract classes, are much closer in behavior to an interface than they are to a base class, but they are a class and not an interface. So Abstract methods themselves are virtual by nature. So all abstract methods are virtual. And the biggest difference between Java and C# in terms of object orientation is that C# allows some methods to be non-virtual, which means that a child class cannot override that method even though the method is implemented by a parent. So in Java, all methods are considered to be virtual. In C#, all methods are considered to be non-virtual unless you use the virtual keyword to indicate that the method can be overridden. So virtual methods allow their implementations to be overridden by derived classes. So anytime you're trying to implement base functionality, like the sound method on an animal, you want the child classes to be able to override the default sound that an animal makes. I guess, I don't know, that would be screaming or something. And if you are not careful, the child classes will not have access to override that behavior unless the parent has marked that method as virtual. And in Java, all methods are virtual just by virtue of being methods. So the purpose of the virtual keyword is to provide this level of security around API methods. So in C#, because the .NET framework is so kind of open and it's so easy to access libraries that allow you to do Lord only knows what, it's very popular to take a third party's public APIs directly from their DLLs, so not necessarily a web API, but really more a wrapper, and take that wrapper and use it to do whatever you actually want to do with their application. And so one of the ways that you can get away from another third party doing that to your libraries is to minimize the number of methods that you make virtual. So if you only have 2 or 3 different methods that you want to allow derived classes to override, you want to make sure that all the rest of them are not marked with the virtual keyword, and that will keep anybody that has access to inherit from that class from overriding non-virtual methods. So the relationship is kind of this. Abstract methods are all virtual, but not all virtual methods are abstract, and not all methods are virtual to begin with. So there are methods that are not virtual, there are methods that are virtual, and there are methods that are abstract, but all abstract methods are virtual, but not all virtual methods are abstract, and not all methods are virtual. That's a mouthful. Going one layer up, you can also use the sealed keyword. So if you have a sealed class, that means that that class can never be used in inheritance at all. So this is a way of getting away with terminating inheritance without making things static. And again, this is another bit of additional control. Basically, you only want to unseal classes that you are using for your application in terms of inheritance, and sealing all the rest of them will give you security against people actually using your classes as base classes for whatever purpose they want. So a little bit about interfaces. So interfaces tend to be a little bit more important for C# than you might expect, largely because of their role in multiple inheritance. But they act and they are theoretically very similar to the object-oriented concepts that you've probably seen before in your life 500 times. So the very tired, very beat down adage is that an interface in object-oriented programming is basically a contract. It's a contract between the interface itself and the class that extends or implements that interface. And so basically interfaces dictate methods, and they dictate data, and they dictate basically any member that you can think of that has to be implemented by a class as long as that class implements that interface. And so they have the same kind of conceptual benefits that you expect from something like Java, And ultimately, in all of these languages, what you're trying to get away with the use of interfaces is loosely coupled design, which allows you to extend the application and kind of maintain the application in a much more cost-effective kind of way. So one of the major ways that we're going to use interfaces in the class is with what are called factory methods. So as long as you have interfaces, you can always use factory methods instead of constructors. And so these are good things to think about going forward as we go through some architecture toward the end of the class. But like I said, they also are an integral part to the workaround for multiple class inheritance. So in general, multiple inheritance happens when you have a single derived class that derives its behavior and derives its data from more than one parent class. C# at its root does not support this idea. So if you try to supply more than one base class for the same class using a comma or whatever, the compiler and the syntax checker will both throw errors and tell you that that is not a good idea, that you can't actually do it. What you can do is you can implement multiple interfaces, and you can inherit one class at the same time. So one of the most popular ways to work around this is to emulate multiple inheritance by implementing more than one interfaces at the same time. And we will look specifically at this workaround in the first code along in this week's module. So in conclusion of all of this, object orientation works exactly the way that you would expect it to work in any sort of modern, I'm going to call it Gen 3.5 kind of language that supports object-oriented programming. The major difference that we've seen so far between C# and Java, is that they use their virtual machines slightly different. They also have differences around things like packages versus assemblies and how to reference assemblies and all of that kind of stuff. But at the root, the biggest kind of behavioral difference that we've seen is that Java assumes that methods are virtual, while C# does not. You have to actually actively tag a virtual method as virtual in order to allow derived classes to override the behavior in that method. So what we're going to do next is go through some really quick design considerations given the object-oriented nature of the language. So we're going to talk a little bit about global variables, why they're not so great. We're also going to talk about some specific things around object orientation which may make your life better or easier when you go into the programming assignment for the end of the week. And then the rest of the week will be focused primarily on code-alongs, which will hopefully give you a kind of hands-on experience for what object orientation allows you to do in C#. So thanks for tuning in, and I hope to see you in the code-along.